and temperature, right? And heat was the total energy of all particles of matter in whatever system you're looking at. Temperature is the average kinetic energy is what we're going to show. Is it's related to the average kinetic energy, the motion of the particles itself. Bless you. And so last time everything we discussed was the different classifications of matter. So the three phases that we'll be concerned with or physical states. And what were those three phases? Solid, liquid, and gas, right? Solid was definite shape plus volume. Liquid was definite shape or volume. Which one was liquid? Definite volume, right? But not definite shape because liquid takes the shape of what? Whatever container it's in. Plus indefinite, abbreviate shape. And then gas was indefinite both, right? Right, so those are three states of matter that we talked about and how we classified them. And then we talked about pure versus mixed substances. And really the main takeaway from that, we talked about elemental versus compounds. The main takeaway from that one is I want to talk about or emphasize the heterogeneous, I don't spell that right, mixture versus homogeneous. Mixture, right? Heterogeneous was what? Coffee. That's it. Yeah, non-uniform properties throughout all of it, right? And it has non-uniform properties. What can we say about that mixture? Why does it have non-uniform properties? Yeah, all the components of the mixture are not in the same phase, meaning some stuff might be liquid and other stuff might be in the gas phase or in the solid phase, right? So an example would be like soup. You have the liquid broth, solid potatoes or something in there, right? So this is going to be non-uniform properties. Did he make it to his classroom, did you see? Dr. Iniguez across the hall? Were the students still waiting outside, or?
No, there's nobody else.
Okay, he made it in. I was supposed to give him a call and I forgot. Non-uniform properties, and then non-uniform phase is another way of saying that. And then a homogeneous mixture then, by contrast, is uniform properties and uniform phase, right? So if we think about, if you grab two parts of the soup mixture, right? Sometimes you only grab some broth and sometimes you might grab a potato, right? So there's not identical and you grab two different sections of that mixture. Whereas if you go with the ocean, you get a liter of ocean from over here and a liter of ocean from over here. Those are going to have the same properties because they're all in the same phase. They have uniform properties between them. Okay, so that's kind of what we ended off with. There was a lot of kind of qualitative definitions of everything. And then we got into a discussion about energy, right? Two forms of energy that we usually discussed were what? Potential and kinetic energy, right? Potential is the energy that's stored, the potential to do work. And then kinetic energy is the energy of motion, right? And these are the two most important energies when we're looking at chemical systems, right? Because we think of potential energy, if we have a ball and we're about to drop it to the ground, it has potential energy because there's the potential to do work as it falls to the ground, but until you release it, it doesn't release that energy. In bonds, in atoms and molecules, we have the same type of potential energy except it's stored in chemical bonds, which is going to be electrostatic in nature, the electronic charges of atoms and molecules interacting with each other. And we'll talk about that more in detail as we get to it, but I just kind of introducing the idea early on. And then where we ended was, again, heat, this description of heat, which is the total energy of all the particles of matter. What that means is the potential plus the kinetic energy terms, and then temperature is the average kinetic energy, right? So how fast things are moving or vibrating, that's related to the temperature of a material. And it makes sense, right? As things heat up, you imagine that they're kind of getting more aggravated and moving around faster. So when you start to boil water, things start to move around, bubbles form. See motion there. All right, any questions about where we left off?
Are we going to go over the heat and temperature a little more?
Yeah, we're gonna have a lot more discussion about what temperature is, what heat is, and how we actually use that in problems, and that's kind of what we're gonna be talking about today, right? So the thermometer is an instrument that's used to measure the temperature, and it usually measures some intrinsic property of a material, something like expansion, right? If you heat something up, what do you think happens to that? Does it contract or does it expand? It expands, right? There's only a couple examples where that doesn't happen, like ice. Water does the opposite, right? That's why ice floats on water. So expansion, we can measure the temperature of something by correlating how much does it expand every time we heat up the material, right? So as we heat stuff, things tend to expand, right? And we use this in analog thermometers, and when I say analog thermometers, I mean like the ones you guys used in labs, right? How do we relate expansion to the thermometer that you guys used in the lab? What do you guys think is expanding? Yeah, the liquid that's in the thermometer, right? So you see that red liquid. It used to be mercury, right? So it's really bad metal. Get that on you, poisons you. Most thermometers these days are just a little bit of food coloring and some sort of alcohol. So what happens, you heat it up, and it expands a certain amount. So the tick marks on the thermometer are calibrated. You got some mathematical equation that says if I heat it up 1 degree, the liquid should expand this much, right? So that's how we measure the temperature of something. And right as we heat it up, the molecules have more kinetic energy. They're trying to move around. They're bumping into each other more, and that's why the liquid itself is expanding. We can also use conductivity, so we can use a digital thermometer, right? And it's still kind of related to expansion. So the way a digital thermometer works is you have a little piece of metal, you stick it in something that's hot, it expands, and what happens is you measure electrical current that goes through that metal, and the current changes based off of how much that metal has expanded itself, right? So related to expansion, but the conductivity is what is measured in a digital thermometer. Right, so the same way in the analog thermometer where you see that how much the liquid rises gives you a temperature, in a digital thermometer, how much the metal expands, right? Does anyone know any real world examples where you have to consider expansions of metals and stuff? Yeah, glasswork, you have to consider expansion of metals, right? If they expand too much, they actually shatter. If anyone knows anything about, jets and whatnot, especially very hypersonic jets that move very fast, those are actually designed to have gaps in the actual metal. So if you fill it up with fuel, it's leaking fuel until the jet gets in the air and is moving really fast. Why is that? Because there's gaps so that once you reach high speeds and things start to heat up, the metal expands and then fits to where it's supposed to be, right? So in actual jet engines and stuff, you have to consider that, the expansion, right? And then how much that metal expands in a digital thermometer is correlated to then a conductivity, right? So it gives a little electrical measurement. That's how a digital thermometer works. And so 3 scales are used for measuring temperature. Does anyone know what the 3 scales are? Fahrenheit is going to be one of them, Celsius, and then Kelvin. Celsius, and then I'll write out the full word here. Fahrenheit. I think I spelled that right. All right, so those are the 3 temperature scales. And then, as you can imagine, we can convert between these 3 temperature scales. Kelvin, I'll put a little star next to, because that's usually what we use in chemistry. We'll look at Celsius here too, but Kelvin is the absolute temperature scale. And the reason we call it the absolute temperature scale is because 0 Kelvin is defined when molecules have 0 kinetic energy. 0 Kelvin equals 0 kinetic energy. Does anyone know what the Celsius scale is defined by? So Celsius is defined based off of properties of water, right? So 0 degrees Celsius is when liquid water turns to ice, and 100 degrees is when liquid water turns to gas, right? So this is scaled by properties of H2O. Kelvin is the absolute temperature scale because 0 Kelvin equals 0 kinetic energy. Celsius is the water temperature scale. In Fahrenheit, I don't know the history of Fahrenheit. It's another scale that people have used. Okay, so how are these different scales related to each other? Well, here we actually have a visual, right? Absolute 0 is minus 273 degrees Celsius, and then Fahrenheit, absolute 0 would be defined as minus 460 degrees Fahrenheit. But you see, right, this is the ice point, and then the steam point up there, so that's why Celsius is related to properties of water. And then for Kelvin, we have, that's going to be 373 Kelvin. And then Fahrenheit is its own scale as well. In general, we'll be looking at mostly Celsius and Kelvin. And so these temperature ranges, 32 to 212, is the same as 0 to 100 for Celsius and 273 to 373 for Kelvin. And so the conversions between them are given by these three equations, right? Kelvin, if you want to solve for the Kelvin using Celsius, you just take degrees Celsius and you add 273 to it, right? So 273 Kelvin is 0 degrees Celsius. Fahrenheit, going from Fahrenheit, between Fahrenheit and Celsius, is 1.8 times degrees Celsius plus 32, right? So this is where you plug in degrees Celsius. This is where you plug in degrees Celsius. And then you can go between Celsius and Fahrenheit, which is degrees Fahrenheit minus 32 divided by 1.8. And so these two equations are just rearranged to give one or the other. And here you would plug in degrees Fahrenheit. And so depending on where you're going and where you're starting, you use one of these equations, right? So this is how you would go from degrees Celsius to Kelvin. This is how you go from degrees Celsius to degrees Fahrenheit, and this is how you go from degrees Fahrenheit to Celsius, right? So from start to end. Alternately, you could use these two, or they just modify, so you're not dealing with 32 there. They just rearranged those equations as well. Okay, so these are just the different relationships between the different temperature scales. In a way, these are kind of like conversion factors, except there's a linear scale between the two. Okay, any questions on that? Or how you would use that? We'll go through an example or two. So the melting point of silver is about 960.8 degrees Celsius. What is this temperature in Kelvin? Right, so we know the relationship between Kelvin and Celsius was degrees Celsius plus 273. So to solve this, all we would do is we would just plug in 960.8 into our equation. So we get 960.8 degrees Celsius plus 273 is going to equal our degrees Kelvin. So this is going to be somewhere in the thousands. And the thing when we're doing these conversions between temperatures, we only consider the temperature given to us for unit conversion, or for significant figures. Right, so whenever we're using any of these equations, we don't use 273 for sig figs. And for example, if we're looking at these other two equations, you wouldn't use 32 or 1.8 degrees for sig figs. So this would then be 960.8 plus 273, which is 1233.8. We should have the same number of sig figs as the temperature we're starting with, which should be 4. So what should our final answer be? 1,234 degrees Kelvin, right? We round up, right? We have 5 sig figs here, so we have to round up this digit because that's larger than 5. So that would be our final answer here. So going between temperature scales is kind of just a lot of plug and chug, right? Which equation do I need to use? Because which temperature am I starting from and where am I going? All right, so here we have another one. Pure iron melts at 100 or 1800 degrees Kelvin. What is this temperature in Celsius? That one's relatively straightforward. You can imagine these could get layered if you're going from Kelvin all the way to Fahrenheit because I didn't give you a direct conversion between those two. All right, so just take 2 minutes and see if you can set that one up. Going from Kelvin to Celsius, so what do we have to do? What equation are we going to start with? K equals Celsius plus 273, right? But we have, we have Kelvin, right? So what do we need to do with this equation? We need to isolate Celsius here because that's what we want to solve for, right? So we subtract what from both sides? Minus 273, minus 273, that gives us degrees Kelvin, minus 273 equals degrees Celsius. So we plug in 1800 minus 273 equals degrees Celsius. What'd you get? 1,527. 527 degrees Celsius is our answer. We have how many sig figs in our original? 4? Or how many do we have? Let's take a look again. We have 2, right? Because those are what kind of zeros? These are going to be trailing zeros before what? Zeros before decimal, which means that they're not significant, right? Not a significant figure. So then how do we round this number? To 2 sig figs, right? So we're going to round it to this digit. This is our rounding digit. Is it less than or equal to 5? Less than, so that should go to, what should 1527 go to? 1,500 degrees Celsius, right? And that'll be our answer for that. So one thing we have to keep track here is sig figs, and then we just had to rearrange this equation. This is a simple equation, or simple relationship, so it didn't take much. We just had to subtract 273 from both sides. All right, any questions on that? No? Okay. So we'll save some for next Monday when we're kind of going over stuff for the exam, and we're going to move on to specific heat. All right, so we have 2 more example problems. We'll use those next week. So specific heat, again, the letter Q is what we defined heat as. Specific heat is a property of a material, and it's usually S, or you might see C sub V, or C sub P might be the different variables you see to represent specific heat. And so what it means is that different materials have different capacities for storing heat. And that's another way you might hear this property called, is the heat capacity of something or the specific heat. And so it makes some sense, right? Because if you have, for example, a piece of metal and you put it on the stove versus a pot filled with water, which one tends to heat up faster? The metal does, right? It gets hot a lot faster, and if we think about if you have some water in there and you're trying to boil it, it takes a lot longer to boil, whereas the metal itself actually gets a lot hotter faster than that. And so that has to do with a property of the material called the specific heat. And what this does is it says basically the energy required to raise 1 gram of that substance by 1 degree Celsius. And of course, you can use this in different degrees of energy and for different temperature scales, right? So this is the amount or the energy of a substance is the amount of heat required. The specific heat of a substance is the amount of heat required, which again, heat was given to in units of energy, to change the temperature of 1 gram of that substance by 1 degree. And so the units of S, for example, right, so remember these brackets we can use. This means units of, or dimensions of, right, we use those interchangeably, are equal to joule per gram Kelvin, or they can be equal to calorie per gram Kelvin, or they can be equal to calorie per gram degrees Celsius, or they can be equal to joule per gram degrees Celsius. Right, so really what they boil down to is that they're in units of, let me move these over a little bit. They boil down to units of energy over mass times temperature. Right, and what we said in words makes sense that these are the units of it, right? It's the energy or the heat required, so the energy you put into it, to change a temperature of 1 gram, the mass of that substance, by 1 degree, right? So that's how we interpret verbally what we set up there into the units of the heat capacity. This is related to how much energy do we need to put into a certain amount of substance to change the kinetic energy of the molecules or atoms in it. Okay, any questions on that? Give you guys a second to think about it. Finish writing. And so, some specific heat of some common substances in the two of the different units that we talked about, right? Calories, grams per degree Celsius, and joules, grams per degree Celsius. We see that on both of these scales, water has higher specific heats than the metals, right? Which is what we said intuitively we kind of feel, right? Because we put a pan on a fire stove that heats up a lot faster than the water inside of it, right? And that has to do with the fact that for metal, it requires less energy to raise the temperature of the metal. Cameron? Yeah. Right, so as we raise the temperature, it requires less energy for metal than it does for water. And does anyone have any idea why that might be? Maybe from previous knowledge or any feeling about it? Maybe our discussion about solids and stuff? Keep good? Okay. Anyone still writing on this one too? So when we have a solid, right, things are bonded and they're very close to each other, right? Which means that as we put energy into it, it's easier for the energy to move from one atom to the next, right? If things are already really close to each other and this one's vibrating really fast, the one right in the neighbor is going to feel it. Whereas in a liquid, for example, this one can be vibrating really fast and this one kind of gets bumped away and moves away. So it loses that transfer of energy, right? So metals and solids tend to be a lot more efficient at transferring energy between the molecules and atoms, which means that their specific heat is going to be lower. And so that should allow us to think about the specific heat and then determine, based off of that value, is it hot faster or cold slower? So when heated substances with a low specific heat get hot faster, while substances with a high specific heat get hot at a slower rate. And if you ever get confused about this, just always go back to the water versus metal analogy. Because when you're looking at water versus metal is going to have a lower specific heat and it gets hot slower. And then when cooled, right, so we can go in the heating up direction, we can also go in the cooling down direction, right? When cooled, substances with a low specific heat cool faster, while substances with a high specific heat cool at a slower rate. And so this one is a little less intuitive, but if you ever have a pot of boiling water versus a pan on the stove, and you put them both on a cool surface, the water's gonna take a lot longer to cool down than the pan will.
And it's because it requires more energy to begin with, right?
Yeah, because it takes more energy, so it takes more energy to heat it up, which means that it's also gonna be less efficient at getting rid of that extra energy too. Once it has that energy, it's gonna hold on to it, but it takes more energy to actually heat it up as well. Okay?
So using the example with water and a dense object, does that mean that dense objects get hot faster?
So you're on the right track, right? Thinking the density when we think about solids versus liquids, right? Solids will generally have higher density, but you do have solids that have lower density than liquids as well, right? You think about, a piece of wood, it's also a solid, but it has a lower density than water, so it floats on water as well. But you're on the right track. That is something to kind of be aware of, right? If it's two solids, most likely the more dense solid will have a lower heat capacity. It's more efficient at transferring energy. Summer?
So, let's say you have two metals.
Mm-hmm.
How would you tell the difference of which one would heat up quicker than the other?
So that's actually, when we talked about digital thermometers, that's actually what you have, right? You have two metals that are close to each other. One's gonna have a different heat capacity, so it'll expand and contract. That's really how you kind of measure how much energy temperature is changing, right? They expand and contract, and then you can see based off of that which one has a lower or higher heat capacity. And another way you could test that, right, is if you just heated up two things, right, and timed how long it took to get to a specific temperature as well. Right, this one, they're getting the same amount of energy at the same rate. Whichever one gets to a higher temperature faster is gonna have a lower heat capacity.
But look, what causes that exactly?
Oh, it has to do with the specific interactions of the molecules and atoms in the solid, right? So we talked a little bit about, it's the kinetic energy. The heat capacity is related to how efficiently can it transfer that energy. Right, so you can imagine that some atoms are very good when they bump into another one, that it'll change, it'll keep going, kind of like billiard balls, right? Like when they transfer energy very efficiently. Some atoms are going to be very good at that, and other atoms and molecules are not going to be as good at that. So it's kind of like an intrinsic property of the material itself. So, some scientists spend a lot of time designing special materials that will do this in one dimension, one direction, but not in another, right? Because sometimes you don't want, there's devices called thermoelectrics, where you can generate electricity by having a temperature difference, right? So if you have something that transfers heat very well, then you don't want that for a thermoelectric, right? Because if you heat up this side, it's gonna transfer all the way to the other side of the material. Then you don't get your electricity anymore. So you design a material that can conduct electricity, but it doesn't transfer heat that well in that direction. And there's, a bunch of other materials that are kind of looking at that too, where they try and have properties that are the same in one direction and not the other direction. So that's kind of like the, struggle when you're designing those types of materials, is that metals tend to be very good conductors of electricity, and it means they're also very good conductors of heat, right? But those two, when you're designing a material like that, they conflict with each other. So I'll write that right here, just in case you're interested in looking into those thermoelectric devices. And so we can actually calculate the amount of heat or energy required to change from one substance to another using the specific heat, right? And so this equation is almost derived exactly from dimensional analysis or unit conversions, right? The units of specific heat were what? Yeah, it was represented by the letter Q, so that's what our equation is going to look like. What were the units of the specific heat of a substance?
Was it the joules?
Yeah, it was the joules. So the units of this were joules, or energy, over mass, yeah, right? So it's true, grams per whatever the temperature is, right? So we'll do grams, degrees Celsius, right? Because that was one of them. So if you were doing a unit conversion and you wanted to say, well, I know the mass of it and I know what the temperature change was, right? How hot and cold it got. What would I have to multiply this by so that I'm only left with units of energy? What would I have to multiply that by to be only left with units of energy? If we're just thinking about units, not even numbers yet. Units of grams, right? So units of grams, and then what else? Times units of temperature. Or we'll do degrees Celsius because that's what I have in the denominator. All right, so if we look at how these units cancel now, all that's left is the unit of energy, which is what this equation is trying to tell us, right? This equation is saying, well, we know how much something weighs. We know the property of it, right? So some scientists spent their PhD determining that number, and then we know what temperature change was. So we can calculate the energy that was required to make that temperature change happen. All right, so this is Q equals M, which is the mass, times S, the specific heat, times delta T. All right, and delta T here means what? Change in temperature, right? So this is the change. So I know I kind of just rewrote what I have in the boxes up there, but in T, and delta T is equal to what? If we were given multiple temperature values, what is delta T equal to? Yep, that's exactly right. Delta T, remember delta of any variable is equal to the final minus the initial. All right, the change in temperature. The place we ended minus the place we started. All right, so I'll always give you this equation, for example, on an exam or a quiz. But if you were out in the wild after you've taken this class, you could figure out this equation just by knowing what the units of this are supposed to be. We can think about that in terms of a unit conversion. So this is our equation for the specific heat of a substance. And so how would we use that? Well, let's say how much heat is needed to raise the temperature of 200 grams of water by 10 degrees Celsius, right? So we're given decimal places here, so it's important to keep track of that for the sig figs. And then we're given the value of the specific heat of water. Right, so here we're given that we're raising the temperature of water by 10 degrees, right? Which means that it doesn't matter where we started or where we ended, because we're already given the range of temperatures. So delta T here is going to be 10 degrees Celsius. The mass we're given, and then the specific heat is a constant that we're given as well. So if we wanted to calculate the specific heat, we have Q equals MS times delta T. We plug that in. 200 grams times 4.184 joules per gram degrees Celsius times 10.0 degrees Celsius. What happens to the units?
The grams cancel.
Grams cancels with grams here. Degrees Celsius cancels with degrees Celsius, right? So we're left with only units of joules, which is our unit of energy, which is what we want, right? So we plug all that in. 200 times 4.184 times 10. And I get Q is equal to 8,368 joules. But we have to keep track of sig figs here. Right, when we're multiplying and dividing, what are the rules for sig figs? Yep, the number with the lowest amount of sig figs gives us the sig figs of our answer. So how much does 200 point have? So because of this decimal place right here, remember there's two ways you could signify that these are significant digits. You either add a decimal place or you underline that last zero, right? So that actually has 3 sig figs. 4.184 has how many? 4 sig figs. And then 10.0 has we have 1, that's significant, right? It's non-zero. This is a trailing 0 after what? Decimal, so is that significant? Yep, and then what about this 0? Now it's sandwiched because it's between 2 significant digits, right? So that's also a significant digit as well. So there's how many? 3 sig figs. So this then gets rounded to what? $8,370 joules. 3 sig figs. And what if I asked you to convert this into kilojoules? How would we do that? We divide by 1,000, that's shorthand, but if we did it the long way, 1 kilojoule equals how many joules? 1,000 joules. So we have our 2 conversion factors, 1 kilojoule per 1,000 joules, and then 1,000 joules per 1 kilojoule. Which one would you use to convert this?
We want joules, right?
Yep. Or we want kilojoules, right? We're converting joules to kilojoules.
Use the first one, right?
We use the left one, right? Because then units of joules cancels out, and we're left with units of kilojoules. So let's see how that works. 8,370 joules times 1 kilojoule per 1,000 joules. Joules cancel out, and we're left with kilojoules, which is what we want, right? So this would then become 8.37 kilojoules, right? It still has 3 sig figs, but we don't include the 0 here, because if we did, that becomes a trailing 0 after what? Decimal, and then it becomes significant, right? So same number of sig figs. The question didn't ask for this in kilojoules, but we're doing that on today's quiz, so good chance to mention that. All right, any questions on this? All right, so
Just to make sure, for that one, the 3 significant figures, if it has that decimal, we have to consider those.
yeah, that's exactly right. So the way that you consider, right, because sometimes you can have a number like this, and then you can say, well, it actually has 2 sig figs here. And the way that you imply that it has 2 sig figs is you just underline that 0 is significant. Or let's say 80 has 2 sig figs, then you can do it one of 2 ways. You can either add that decimal, or you can have it as 80 and then underline that 0. I'm usually not going to give you something like that, but in general, if you see those two, that means that becomes significant, right? If the decimal is included, then it means all the zeros before that have to be significant. If there's no decimal and it's just underlined, that means that it goes up to that point for the significant figures. And I don't think I gave you anything like that on the quiz. This is just for, when you see this in the future, right? Or in future classes, that's what that means. Okay, so before we go on, all right, so here's another example. So calculate the specific heat of a solid. So here we're going to be asking in a different way. Question? This one? Oh yeah, of course. Yeah, if we're going too fast, don't hesitate. One more, yeah. Yesterday I had a lecture and 2 more? This way? This one, I see someone else trying to take a picture too. One more, this one? Okay. I was giving a lecture before lab and I had to use the bathroom really bad, so I'm pretty sure the recording is like evenly paced, and then towards the end like trying to rush through the last little bit. Okay. And so, so it was the next example. So I'll let you guys think about this one for a second. So here you're given how much energy you put into it. You're saying, I know I put this much energy into it. And I know that it changed the temperature by a certain amount, and I know how, and I weighed it, so I know how much it is, or how much of the substance is there. And saying, what is the actual property of this material, right? So you can use this to inherently calculate the material properties. The same way we're calculating density, you can calculate the specific heat of whatever substance it is that you're looking at. All right, so think about what you're given and what you have to do with that equation.
Times specific heat
Yep.
times, what is delta T again?
The final temperature minus the initial temperature. But when a question phrases it like this, so this one it actually does phrase it, and it gives you two temperatures, right? But the previous question, it phrased it, and it said, to give you a change in temperature of 10 degrees. When it says it that way, it's saying you already know what the change is gonna be. But here they're saying we specifically went from this temperature to that temperature. So we actually know we have to solve for what delta T equals to. So that's good to identify then what you have there and what you need to solve for. So they have a value here, but you have to actually see how they calculated that. All right, so you're given Q here, you're given the mass, and you're given delta T, right? Delta T is equal to, in this case, 52.6 degrees Celsius minus 25.0 degrees Celsius, right? And that's how this number here became. So if we want to solve for S, what do we have to do to this equation? Ms delta T. What do we have to do with this? We have to isolate S. We want to solve for S, right? So what do we do to both sides of this equation?
You divide by
We,
mass and change it.
Yep, we divide by the mass and we divide by the change in temperature. Both sides, right? And when we do that, what happens to those on the right-hand side of this equation? That cancels out. That cancels out. So what we're left with is Q over M delta T equals S. So we can plug in values for that. 1638 joules divided by 125 grams. We always include our units. Divided by 27.6 degrees Celsius. And so we plug those in, we get 1638 divided by 125 divided by 27.6, and I get S equals 47, or 0.475 joules per gram degrees Celsius. So I wrote my units here. Do these units make sense for heat capacity? Right, there should always be energy over mass over temperature, right? So these units make sense. The units always tell us that we're on the right track, right? We're trying to calculate mass and we end up with units of temperature, we made a mistake somewhere. Right, so always checking for our units. So this gives us the heat capacity for this material. All right, so this one is the same idea, it's just rearranged a little bit. And so up until this, well, even for this problem, we've been talking about, putting heat directly into a substance. So this can actually be taken advantage of because energy, the first law of thermodynamics says energy can't be created or it can't be destroyed. It just gets converted from one form to another. So let's say that we didn't know the heat capacity of something we can take advantage of this transfer of energy to then transfer this energy to something we do know the heat capacity of, and that allows us to solve for the energy in that material. And so that's a lot of words, but what I mean by that, and that's where we'll end off with today's lecture. So we have another example, we'll go over that after that. But in energy and nutrition, you can use what's called a calorimeter, right? And what this is you put a sample of food or something in there, and then you ignite it and you burn it, right? When you burn it, it releases what? What do you guys think it releases? Heat, right? It releases energy in the form of heat that then, if you put your hand next to it, what would that feel like? Hot, right? You don't know the specific heat of a sandwich or something, right? So you don't really know, you can't directly measure the energy that's being released from it. But if you put water around it, we know the specific heat of water. That water feels that same heat, right? And the energy gets transferred into the water. And you could take advantage of that to calculate the change in temperature of the water around it to then give you the energy that was released by the food. And so this is a long-winded way of saying that the energy or the heat absorbed by H2O is equal to the heat minus the heat released by the food. Right, so the energy, right, if we have a closed system, we put, some insulating material around it so the temperature can't go anywhere else except into the water around it. Right, so the temperature or the heat released when we burn the food gets released into the water, and if we add energy to the water, what happens to the water? What changes? The temperature, right? So energy is moving into the water, which means the temperature of the water changes. So if you know how much the water temperature changes, you know the mass of the water because you know how much water you put in there, and you know the heat capacity, then you know what variable on the slide there. Right? If we know the mass, we know the heat capacity, and we know the change in temperature. Then we know the heat that was absorbed by the water. And so it's an indirect way of measuring how much was released by the food, right? Units of energy or calories, which are common for food, or joules. So we can get our caloric content from food by measuring the heat absorbed by the water in a calorimeter. So we'll probably do an example of this actually in the lab, and it'll start to make more sense. But right now I'm just introducing this idea to you, right? We can take advantage of the fact that we know the heat capacity of something, we know the mass, and we know the change in temperature because we put a thermometer in it. We can measure the heat released by anything by putting it in a system and allowing that energy to transfer into the water. And so that's the idea behind a bomb calorimeter. And so we'll go over an example of that on Monday. All right, so we'll end this discussion on energy and heat